And as you see, we have a block and some loading on the block. And we need to find the stresses at point B and D. Okay. All of you can see the screen now? Okay. Yeah, Dongling, if you want to do it again, you can do it again. Okay. So now I will start doing this example with you. Do you want to try, or I do the example directly? Okay. So stop sharing this screen. So now for example 1, question 1, we have a block, rectangular cross-section block, like that. And this is the axis of this block. This is x-axis, and this is y-axis. So this is the centroid of this cross-section because it is rectangular. We have one applied load here on the edge. The load here is 40 kilonewton. The distance or the dimension of this block is 200, so the total dimension is 400. Also, this block in this direction, we have 400 millimeter. So the total dimension here is 800 millimeter. Okay, so this is the block and the forces we have on the block. The requirement is to find stresses at point B and point D. Where is point B and D? Point B and D are somewhere here. Here is point D, and here is point B. Okay, so we need to find the stresses at point B and D. If you have a look on this block, you need to simplify this. So if we draw the horizontal projection of this cross section, so this is our cross section, rectangular section. The dimension of this block or the cross section is 800 millimeter times 400 millimeter. So this is the dimension. This is the axis. So I will just need to rotate this one. Okay, I will do it again. So because the x-axis is the horizontal axis, just to match with what we have done before. So this is our cross section. The dimension is 400 millimeter times 800 millimeter height. Okay, the axes are y axis and x axis. Here is the centroid of the section because it is regular shape. So this is the CG. The force, the applied force is 1 point load here, perpendicular to the screen. And how much is the load 40 kilonewton. I will represent this with a cross. So this means the force is perpendicular to here and going inward or downward. Okay, so this is the cross section and the loads applied. To find the stresses, here we need first to find the probabilities of the material, Any section, any cross section, we need probability of material before proceeding. So what probabilities we need here? We need A and IX. If I ask you to find A and IX and even IY, if we have to find these three, can anyone tell me how to find these three probabilities? If we want to find A, how much A for this cross section? It is a rectangular cross section, so A will be 400 times 800 millimeter. So it will be 32,0040 millimeter to the power 2. So this is this is A. For IX, here the centroid of the shape is the centroid of the whole shape. So IX will be BH to the power 3 divided by 12, which is here X. So X, B is the parallel to X, which is 400. This is B. H is the perpendicular to X, so this is the perpendicular. So we have 400 times 800 to the power 3 divided by 12. This is IX. So IX will be 400 times 800 to the power 3 divided by 12. Will give us 170.66 times 10 to the power 8 millimeter to the power 4. Okay. The last one is IY. How can we find IY? IY will be HB to the power 3 divided by 12. Y, so the H is the parallel to Y, which is 800. B is the perpendicular to Y, which is 400. So it will be 800 times 400 to the power 3 divided by 12. This will give us 66.66 times 10 to the power 6 millimeter to the power 4. So this is the three properties of the material we need for this cross section, A and IX and IY. So now we can proceed to find the stresses. Do you have any question for the properties? Is there any question? Okay, so now this is our cross section again. This is x-axis, y-axis. This is a centroid. We find that A equal to 3240 millimeter to the power 2. IX equal to 170.66 times 10 to the power 8 millimeter to the power 4. IY equal to 66066 times 10 to the power 6 millimeter to the power 4. So this is our probabilities. The dimension of the section, again, this 400 millimeter and this is 800 millimeter. And we have a load here, compression load here, equal to 40 kilonewton. Okay. What type of stresses you expect on this cross section? First of all, we have a force here acting far from the centroid. So again, if this is a 3D, this is our centroid, and this is our force. The force is acting out of the centroid. So this force will cause two stresses, or will affect us. Will not be only a force, axial force or a compression force. This force, we cannot deal with it out of the centroid. So we need to move it to the centroid. When we move it to the centroid, we will move it with a force. So this force will be moved to the centroid with a force and with a moment. So we can cancel this force like that and apply a force B and moment M. So because the force B not acting at centroid, so we will replace B with B and moment. So B will be replaced with B at centroid plus moment. How much is this moment? The moment will be the force distance B times eccentricity E, where E is the eccentricity. Eccentricity means the distance between the centroid to the force. Okay, so this is E. So if we have, if we have force out of the centroid, we need to remove this force and replace it with two things. First thing is B at centroid and moment equal to B times E, where E is the eccentricity. Okay, so this load is called eccentric load. So we have two types of loads, concentric and eccentric load. Concentric means at CG, eccentric means out of CG. Concentric means we can only deal with normal force. Eccentric means we have normal force and moment, okay? And this is the difference between them. If the load is here, so this is N, so this is concentric. Here, if the load is here, so this means concentric load. So we have this load is out of centroid, so it is called eccentric load, and we need to replace this load with a moment and a force N. Okay, so now this is our cross section, what is given to us. X-axis, Y-axis. This is the load given to us here, N equal to 40 kilonewton. This one will be equivalent to, what we will do is just X-axis, Y-axis. We will replace this normal force here and replace it with a moment and a normal force here, N equal to 40. Okay, what else we need to add as a replacement for this normal force? We need to add a moment in this direction. This M equal to N or B times E. How much E in this case? E is the eccentricity from CG to load. Okay, here E equal to from centroid to load is the distance, which is E equal to how much? The whole section is 800, 400 above and 400 below the centroid. So E equal to 400 millimeter. So E equal to 400 millimeter. So now the moment will be N or B equal to 40 kilonewton times 400 millimeter. So the moment will be 16,000 kilonewton millimeter. If you want to make it kilonewton meter, so it will be 16 kilonewton meter. Okay. This moment is moment rotating about mx or my. We need to discuss about this moment. This moment is about mx or about my. This moment is rotating about mx. As you can see, the moment is rotating about mx. So this is called mx. Okay. Because the force has distance from x. Does this force has distance from y axis? No, because the force is lying on or located on y axis. So there is no eccentricity from y axis. The eccentricity is only from x axis. That's why it is moment about x. So mx. What else we need to know? Why I put the direction like that? Why I put the tail on the top and the head on the bottom? Why not the reverse? Why not like that? As you can see, the force is pushing down under x-axis. So that's why we need to the head of the section, the head of the moment here is following the force in. So the head following the force. If the force is going down, so the moment head will go down. Okay. So now this means that we have to find the stresses at point B and D for this case. So finally, we have found that this is our cross section given y-axis, x-axis. It is given to us as we have normal force here equal to 40 kilonewton and moment mx equal to 16 kilonewton meter. And we need to find the stresses at point B and D. Okay, here is point D from the head of the question. Here is point D, and here is point B. Okay. Do you have any question about this? How to find the stresses? This is a combination of normal force plus moment. The first tutorial, if you remember from the tutorial of normal stresses, we have normal stresses due to n, which was n divided by a, and we call it sigma n. So we have sigma n equal to n by a divided by a, and sigma for moment mx equal to mx times y divided by ix. So this is sigma m. So the total stress here will be sigma due to n, sigma due to m. So sigma will be sigma n plus sigma mx equal to n by a plus mx y divided by ix. And this is the idea, and that's why it's called combined stress, because we have two types of stresses and they are combined together to give us the final or the total stress. Okay, that is why we at the beginning of the question we have calculate A and we have calculate Ix because we have N and My, Mx. So now if I ask you to calculate the stresses, for this section, Y and XX N equal to 40 kilonewton and Mx equal to 16 kilonewton meter. And again, we have calculate A 32,000 millimeter to the power 2. Ix equal to 1706 times 10 to the power 8 millimeter to the power 4. So now if we calculate sigma n equal to n divided by A. So n equal to 40 kilonewton divided by 32,320,000 millimeter to the power 4. So this in millimeter square, this in kilonewton. So it's better to calculate all the stresses in Newton and millimeter. So how can we convert? We need to multiply this by 10 to the power 10 to the power 3 to make it Newton. So the final result will be in Newton millimeter. So sigma n equal to negative, 0.125 Newton per millimeter square. This is the stress. The stress due to normal force can be tension or compression. Tension positive, compression is negative. What is the sign of this stresses? Is this force compression or tension? Do you know? Anybody can answer? Okay, this force is going downward or pushing the section or going into the section. So this force is compression. So that's why this stress is negative stress. Okay, so the stress due to N here is negative. Now time for sigma mx. Sigma due to mx will be mx times y divided by ix. Okay, so how much mx equal to 16 times 10 to the power 6 to make it Newton and millimeter. So 10 to the power 6 divided by I equal to 170.66 times 10 to the power 6. What is y? Y is the distance from the point, from the CG. Here is the CG to the point. So if this point B, so this is YB. If this point D, so this is YD. Okay, so Y is the distance from the point of calculation to the centroid. So if we want to calculate for B first, why here we don't include anything for B or D? Because the equation or the formula doesn't contain anything related to the distance from the centroid. This means that sigma n is, this value is for all points of the cross section. So any point in the cross section has same stress because this stress is a uniform stress. But for the moment, the stress is related to the distance from the centroid. That's why we have two values. We will have two values, YB and YD. If we want to calculate at B, how much YB? YB is 400 millimeter. So YB is 400 millimeter. If you calculate this stress, you will find this stress equal to 0.375 Newton per millimeter square. Again, the stress from the moment can be tension or compression because any moment make tension in one side and compression in one side. For point B is here on the top part of the cross section. The top part of cross section under tension or compression. This part is under tension. Why tension? Because the moment here, this is the tail of the moment. So the moment are causing tension on the top part. So the stress on the top part is positive. So sigma B is positive. If we want to calculate sigma mx at D, sigma mx at D equal to same formula mx times y d divided by ix. Mx equal to 16 times 10 to the power 6 divided by 17006 170.66 times 10 to the power 6. How much yd here? Yd is the distance again from D to the centroid. So this is the distance. How much is the distance? 400 millimeter. So again, yd equal to 700 millimeter. Okay, so if we calculate this, it will be 0.375 Newton per millimeter square. But if this tension or compression, if you look here, this bottom part of the cross section below the data is under compression. So all this part under compression because this is the moment head. The moment head is causing compression. So all the bottom part is under compression. So the sign of this stress is negative because it is compression. So the top point B is under tension, point D is under compression. Okay. Do you have any problem with that? So now we find sigma n and sigma mx at B, sigma my at D. So if we calculate sigma total at B, sigma total at B will be sigma n plus sigma mx at B. So it will be negative 1.125 plus 0.375. This will give us plus or tension 0.25 Newton per millimeter square. So the stress at point B equal to 0.25 tension. Sigma total at D will be sigma n again plus sigma mx at D. So it will be negative 0.125, negative 0.375. This will give us negative 0.5 Newton millimeter. So the stress at B equal to positive, the stress at D equal to negative 0.5. Positive means tension, negative here means compression. Okay. Do you have any question about this? Do you have any question about this calculations? So this is what is meant by combined action. We have two stresses and we combine them together. Okay. The last step here, I need to show you how to draw the stress distribution over this type of section or this under this type of forces. Okay. So now, if we have a look here again, this is our cross section. This is x-axis and this is y-axis. And this is the centroid. Okay. The forces we have again is N and M. N equal to 40 kilonewton, M equal to 13 kilonewton meter. This is Mx. Okay, thank you, Scan. So now we want to draw, if we want to draw the stress distribution on cross section. Okay. What we will do is draw the stress distribution over on the cross section or over the cross section. First of all, we will draw for normal force sigma n first, then for moment sigma mx, then the final stress sigma total. Okay, what we need to do is first draw datums or guidelines. This is our datum parallel to the moment. So if the moment is vertical, so our datums will be vertical. Okay, sigma n, the value of sigma n was 0.25 Newton per millimeter square. It is constant over the whole section. So if we draw this, I will draw it here. So this is how to represent the stress. The value of this stress is 0.25 Newton per millimeter square. Okay, and we need to extend our, this is line is our centroid. So any point on the cross section here or here, whatever, how much is the value of the stress? The value of stress is equal to 0.25. This is what is mean by constant stresses or uniform stresses. For moment, as you see before in the last calculation, we calculate the value here as 0.375 positive. Here was 0.375 negative. So if we connect them together, so this is positive and this negative. So the value at the middle or at the cross section should be 0. Why the value here is 0? Because sigma mx equal to mx times y divided by ix. At CG, y equal to 0. So the stress should be 0. So this is the stress from normal force will be all the time constant value. The stress due to moment will be all the time linear value. If we want to the combination of this, what is the combination? The combination will be also linear, but how can we combine this together? We will sum the values for 2 or 3 points, because if the relation is linear, so we need 2 points to connect them to find the stress over the whole section. So if we want the combination at the top point, here is negative 0.125, here is negative 125, here is plus 0.375. So the resultant will be 0.25 Newton per millimeter square. If we are here at the centroid, the value here is negative 0.25, here is 0. So the value here will be negative 125, and we connect them. If we need another value for confirmation or for finalizing it, here, negative 0.25, negative 0.375, so it will be, the resultant here will be 0.5 Newton per millimeter square. If we connect these 3 points together, so the value on the top part is positive, the value on the bottom part is negative. So this is the stress distribution on cross section. Okay, did you get that? Do you have any problem with that? Okay, guys, thank you. Now I will stop sharing this one.